Okay, so our next lesson is going to be the statement and proof of Hall's matching theorem. Uh, Maybe before I even get into the nitty gritty here, let me back up and give some motivation. So this is a very natural problem that really does have a lot of lots of application. I mean, kind of lots of application in math is maybe what I'm thinking about, but also there are real world places where these kinds of things apply. So I want to imagine a case where maybe we're running a company and we have certain jobs that need to get taken care of. Let's say there are 6 jobs, and we have some employees. I'll just say people. There can be 7 people. And now what I want to do is I want to make a graph out of this. It's going to be a bipartite graph. Of course, not all jobs can be done by all of the different all of the employees. So maybe certain tasks maybe you need people trained to do. So what I'm going to do is form a natural bipartite graph here. I'm going to add an edge between a job and a person if that person knows how to do the job. So maybe this first person can do these things. Let's see. Let's see. There. Okay. So there's a sensible graph. And what would we like to do? Well, of course, I'd like to assign jobs to people. Let's assume that I'd like to do this in such a way that all of the jobs do actually get assigned. So, or each job is getting given to a person. And I'd like for no person to get 2 jobs. I'd like to arrange that each person has at most 1 job that they're responsible for. So that way I can get all of these jobs underway at the same time. And so a natural question is, well, is this possible? And what we're going to do today is a really pretty graph theory theorem due to Marshall Hall, and it will tell us precisely when this thing is possible. I'm actually going to go ahead and show you an obvious obstruction here. So it turns out the graph that I've formed here, there's a big problem. What's the big problem here? Well, if I look at these 3 jobs, you can see that there are only 2 people over there who know how to do any of those 3 jobs, right? So this, these 2 people down here at the bottom, those are the only 2 people that know how to do any of those 3 jobs. Right, so there is no way I'm going to be able to match up these jobs. Those 3 jobs all need to get done by different people, but there are only 2 people who are trained to do any of those 3, so we're out of luck. So this this thing I'm asking for is just simply not going to be possible. And what we're going to prove is that, in fact, this is the only obstruction. So if you have a bipartite graph and you don't have this kind of an obstruction, then you are going to be guaranteed this this kind of an assignment. Now, let me say what the assignment is here. If we want to pair up jobs with people, well, if I'm only selecting, I'm going to be selecting edges from this graph, right? Because when you have a person who can do a job, that's indicated in our graph by an edge. So what I'd like to be doing in this graph is I'd like to be selecting some edges. And what are those edges going to look like? Well, again, I mean, each job is only getting assigned to 1 person. So we want the job to be incident with at most one edge, and each person should be doing at most one job. So again, the edges that I'm selecting here that are indicating who's going to do what job, those should be a matching, right? What I'm hoping to find in this graph is a matching in this graph, but I want that matching to have the property that when I look at that matching, every vertex of this on this job set is incident with an edge of the matching. So all I'm going to do now is I'm going to introduce a little bit of terminology that will allow us to state this precisely. So again, the thing that we're looking for here, this was a fail here. But what I'd like would be I'll just draw a smaller case, which would be good. What I'd like to do here is I'd like to select some edges here from my graph that form a matching with the special property that every vertex from the set on the left is incident with an edge in this matching. Right, so that's what I want. I want to find a matching with this property, and in this case, I couldn't for this reason we see. Anyway, what I want to do now is just introduce a little bit of terminology that will allow me to describe the things that we want, and then we'll be able to state the theorem precisely, and then we'll head on to prove the theorem. Okay, so first up is the notion of neighbors. I've been sort of informally using this already. If I give you a subset of vertices of a graph, the neighbors of X, that's the set. I denote by n of X. This is the set of all vertices that are not in X that are incident or adjacent to I should say adjacent. So the set of all vertices not in X that are adjacent to a point in X. V is adjacent to a vertex in X. Right. And for convenience, if I just give you a set of, like for a single vertex, I'm going to define n of X to be n of that singleton. Right, so the neighbor set of a vertex X, those are just all the vertices that are adjacent to X. And with that notation, you can see what's going on here. If I declare this set of vertices on the left to be X, these vertices over here, this set is going to be n of X. Right, those are the set of all vertices in the graph that are not one of those three in my set X that are adjacent to one of those three. So what's going wrong in this instance, the reason we couldn't find this matching with the desired properties is that this set X on the subset of our jobs has the feature that the size of n of X is just smaller than the size of X. And whenever that happens, we're just going to be out of luck if we're hoping for this kind of a matching. Okay. So this is one new definition here, the neighbors. There's one more concept. It's an easy one. Sometimes this gets called hitting. I'm going to call it covering just because I'm following West's books. I'll say a subset of edges. This covers a set of vertices. If every vertex in X is incident with an edge in S. Ooh, what am I writing? Right, so a subset of edges covers a set of vertices if every vertex in that set is incident with an edge in S. So you can see what I want here, what I wanted here, and now in graph theory terminology, I wanted a matching that covers the jobs. Oops. If I could find a matching that covered jobs, then I would, that would be my assignment, right? That matching that covered jobs, that's a collection of edges, right? So that an edge just tells me which person is doing which job. Because it's a matching, well, that means each job is getting done by at most one person, and each person is doing at most one job. But because that matching covers the jobs, that means that in fact each job is going to be assigned to someone. Right, so if you found a matching in a bipartite graph like this, if I have jobs and people, and you found a matching that covered jobs, that would be exactly what we're looking for. That's a selection of edges that's gonna you're gonna pick out one edge incident with each of the jobs, and for each of the people over here, you're gonna have at most one edge of this matching incident with them. So that's going to be an assignment of jobs to people in such a way that each job gets assigned, and and each job is done by a distinct person. So no one person gets assigned to do the two different jobs. So that's what we're looking for here. I want a matching that covers the set of jobs. We also have cover notation for vertices. It's the same thing. If I give you a subset of vertices, I say this covers a subset of edges S if every edge in S is incident to some vertex in X. You could use the word hit as well if you want to think about incidents, like I give you a set of vertices and a set of edges. So again, if I give you a subset of edges, we'll say that subset of edges covers a set of vertices if every vertex in that set is incident with one of these guys, and vice versa. Okay, so and again, for our purposes, we're going to be looking at matchings in bipartite graphs, and we're going to be interested in matchings that cover one whole side of the bipartition. And yeah, as you see, this is coming straight away from this kind of job assignment problem. Frequently, this gets called, this is done with like boys and girls. So you can imagine there are girls on the left and boys on the right, and we put an edge between them if that girl and that boy would like to dance together. And then you can ask, well, can we arrange that all of the girls are paired up with boys and dancing at the same time to the same song? And that's exactly the same problem. So this is known as Hall's matching theorem, and it's a very pretty result. It's also very, very fundamental. I'm sort of casting it as a problem that might have some real world implication, and indeed it does. But this is also it's really bread and butter important combinatorial theory. So, okay, so I think I have got all of this stuff out here. Let me state the theorem formally. So again, what we're going to be doing is we're going to be in the context of a bipartite graph, and we're going to be looking for a matching in this bipartite graph that covers the whole left-hand side. So our formal statement of the theorem is going to be as follows. G is going to be a bipartite graph with bipartition A comma B. And what we want is a matching that covers A. And the theorem is going to be there exists a matching covering A if and only if there does not exist this obvious obstruction. So again, the obvious obstruction is a subset of A that we call X with the property that the size of the neighbor set of X is smaller than X. Right? So there we are. So I'm going to give you a bipartite graph, bipartition AB. I would like to find a matching that covers all of A, right? So I'm going to select a whole bunch of edges, and the rule is that every vertex in A is going to be incident with exactly one of these, and every vertex in B is incident with at most one of them. Right? That's what it means to have a matching that covers A. So that's what I'd like. This theorem, oh, this is due to Hall. This is going to tell me that that always exists unless you have this obvious obstruction, unless you have a subset of A, say X, so that the neighbor set of X, right, the set of all vertices in B that are incident with, that are adjacent to some vertex in that set X, if that neighbor set is smaller than the size of X itself, then you're out of luck. Simply, if you want to pick up one edge incident with each of these vertices, well, the other endpoint is always going to be in this neighbor set, and we're going to have a pigeonhole problem. You just won't be able to get a matching with that property. So, so that's our theorem. As I said, I've said this is a nice for real world stuff. It's also very nice combinatorially, and the proof is also very very instructive. So now the if direction here is oh, I see. Yeah, okay. Sorry, the only if here is trivial, the way I've done this. I stated the theorem slightly differently than I did in the notes. Yeah, anyway, in this case, the only if theorem is obvious. So if you have a matching covering A, that's going to imply that that there does not exist a subset of A with smaller neighbor set than X. So again, this is just a excuse me. This is just a pigeonhole principal observation. So the if direction is it's the interesting part. So now I want to assume that there's no bad subset. So whenever you look at a subset X of A, the size of the neighbor set is at least, and I want to show that that means you get a perfect matching. Okay, so for this if direction, what we're going to do is we're just going to choose a maximum matching of the graph. Now, I'm trying to show there's a matching covering A. If M covers A, then we're done. So if M covers A, then we're done. So we can assume that it doesn't. So I can choose a vertex U that's in the set A that's not covered by M. Okay, so we picked the biggest matching in the graph that we could find. I'm now choosing a vertex in A that's not covered by that matching. And now I'm going to be defining two sets based on that choice. And for this purpose, you're going to need to remember the notion of an alternating path. So remember, when I've got a fixed matching M, a path in my graph is alternating if every other edge of the path is in the matching. And there's a special kind of alternating path called an augmenting path. If you have a path that's alternating, but it has the feature that the first vertex and the last vertex, not only are the first and last edge not in the matching, so it's going to be alternating, but you start out with an edge not in the matching, then an edge that's in the matching, then not, then in, then not. So you're going to start out with an edge that's not in the matching and end with an edge that's not in the matching. But it has an even stronger property that those two end vertices, they are not incident with any edge of the matching. When you have that kind of path, that augmenting path, then you can switch the behavior of your matching on that path. So you can take the edges of this path that are in the matching and remove them from the matching, and the edges of this path that are not in the matching and add them to the matching, and that gives you a larger matching. So if you have an augmenting path, then you can increase the size of your matching. Now, we have chosen a maximum matching. So we've chosen a matching of maximum size, and that means that there cannot be any augmenting path. But what we're going to be, and what we're going to do is we're going to take advantage of that, right? So we know that there's no augmenting path, and what we're going to do is we're going to start looking at some kinds of alternating paths. And in fact, what we're going to do is we're going to fix that vertex U, and we're going to look at alternating paths that start at the vertex U. Now, of course, because my graph is bipartite, if you start at U and start walking along path, you're bouncing back and forth every time. In fact, we can really see what sort of thing is going to happen here. So here's my little vertex U. Oh. So this is going to be A, and over here is going to be B. And maybe what I'll do is distinguish the matching. Let me look at an alternating path. So my matching, I'm going to use red for the matching edges and green for the ordinary edges. So if you think about an alternating path, an M alternating path starting at U, this is kind of what it's going to look like, right? If it's an M alternating path, then every second edge that you take has got to be a matching edge. Now, so every other edge of the path will be an edge that's in the matching. So my matching here is indicated in red. Now what's happening here is that because the vertex U is not covered by my matching, there's no edge of the matching incident with U. And that means that however you start at U and start along some alternating path, well, the first edge you take will not be in the matching, so the next one will. And then the next one will not, and the next one will. And you can see there's a kind of parity condition here, right? So when we, if I start at this vertex U, when I follow along a edge that's, when I follow along this edge that's not in the matching, I end up at B. But when I follow the next edge, I'm going along a matching edge from B back to A. So what you can see in this path, in this alternating path, is every time I'm going from A to B, I'm going on an edge that's not in the matching. And every time I'm going from B back to A, I'm going along an edge that is in the matching. That's just got to be just by parity here. Again, as we walk, we alternate between A and B, and as you walk along edges, you're alternating between edges that are in the matching and edges that are not. Because the vertex U is not covered by the matching, that first edge that you take from U over to some vertex in B, that's not in the matching. So if you want to follow along an M alternating path, the next edge you take will be an edge that brings you from B back to A, and it will be an edge that is in the matching. Right, okay. So those are the kinds of paths I'm going to consider, and what I'm going to be doing is I'm going to be dividing up my world into some sets. So let's make some definitions. I'm going to define X to be the set of all vertices in A, so that there's an M alternating path from U to X. And Y is going to be the same thing, but over on the B side. Right. This is a kind of thing that we saw before in a connectedness setting, right? Like I take all the vertices that have a walk to the vertex X or something like that. So we're doing a kind of similar game here, but it's relative to a certain matching, and we're only looking at certain types of paths here. Let me note that the vertex U does lie in the set X. you're perfectly welcome to have an alternating path consisting only of the vertex u. Perfectly valid alternating path. Right, and so now what we've got, we're going to get some subset over here of vertices in B that you can reach by an alternating path starting from U, and some set of vertices over here in A that you can reach starting at U and walking along an alternating path. Now, what I'd like to do is I'd like to look at the behavior of the matching here relative to my set X and my set Y. Now, let's do the following. Let's look at an arbitrary vertex that's in Y. I'm just looking for a good color. Okay. Let's look for an arbitrary vertex. Oh, that's not a very arbitrary one. Let me pick one a little bit further out. So there's some little vertex out here. I'm going to call this one little y. Now, there's an alternating path that walks from you along to that little vertex y. Now, I'm just going to call that path P for the moment just to get a grip on it. So there's some little path P. In fact, maybe I'll just draw it over here. Yeah, let me sort of draw it without quite so much stuff around. Now, so there's my path. It's an M alternating path that starts at U and ends at Y. Now, as we said, this matching that we've chosen M, this is a maximum matching. And that means there cannot be an M augmenting path. Now, what I've drawn here would be an M augmenting path unless the vertex Y is incident with some edge of the matching. Right? So again, if there is no edge of the matching incident with Y, then, well, I found a nice alternating path that starts at U and ends at Y. But because U and Y are not incident with any edge of the matching M, it means I can just flip the behavior of the matching on that path and I'd get a larger matching. And that's a contradiction. I chose a maximum, that means a maximum size matching in my graph. And that means that this vertex Y, it must be incident with an edge of the matching. So in other words, anytime I come to a vertex that's in my set Y along an M alternating path, I can always step back into the set A using that matching edge. Now, from what you see in this path, where can that matching edge go? Well, it can't go to U because U is not incident with an edge of the matching. It can't go to any of these earlier vertices on the path because we already see their matching edges, right? These two vertices of my path over here, this one and this one, well, we can already see the matching edges that they're incident. We can already see red edges, matching edges that they're incident with. Those could not possibly be the edge of the matching incident with Y. So that means you can always walk along Y to some other vertex on this other side. So in other words, what we've just observed is that when you look at, let me just sort of, sorry, space is so limited here, and I want to keep these definitions up. So let me try to just say what we've observed here. So we've defined this set X, all the vertices you can reach from U by way of an alternating path, an M alternating path. We have a similar set Y. What we've just shown is that whenever you take a vertex over here in Y, it's going to be incident with an edge of the matching, and that edge of the matching, the other end of that edge is going to be an X, right? That's exactly what we see here. When we took our path that went to Y, there's some matching edge incident with Y. We can follow along that edge. We're going to get to another vertex on the left-hand side in the set A, and it's going to be another alternating path. That's just allowing us to extend our alternating path. So what that means is that if you look at the matching, M, every vertex in Y is incident with a matching edge, and moreover, the other end of that matching edge is always in X. This has a very nice consequence. Maybe I didn't draw this as well as I could have, but this has a very nice consequence because U is over there too, right? Every vertex in Y is incident with a matching edge. That edge of the matching, its other end is in X. And, but in addition to that, the starting point, our base point U, is also in the set X, and it's not matched. It's not incident with any edge of the matching. And so we've got a wonderful property here. We've learned that Y has to have smaller size than X, right? Every vertex in Y is going to be matched with a distinct vertex in X, but the set X contains not only those edges, but also the vertex U. So what we've learned is, and this is our big observation here, I'm just going to erase some stuff and then write this down. So our big observation here is that the size of X is greater than the size of Y. All right, so in fact, again, every vertex in Y, if you look at the matching M, it's going to be incident with one of those edges in M. The other end of that edge is going to be in the set X, and that gives us a matching between every vertex in Y and some of X, but there's more of X because the vertex U is also in X. And that means that the set X is actually strictly larger than the set Y. Now what I claim is that the neighbor set of X is a subset of Y. So what I'm claiming is that for every vertex in X, all of the neighbors of X, they're just a subset of Y. If we can prove that, then we're going to be done, because that means the cardinality, the size of the neighbor set of X, well, it's got to be less than or equal to the size of Y, and that's strictly less than the size of X. So if you combine this observation and claim, that would imply that this set X has that obvious flaw. This set X has that flaw that the total set of neighbors of X has size less than the size of X. And that's this situation where, you have 3 jobs, but there are only 2 people in the whole company that know how to do any of those 3. And well, then you can't, you can't assign all 3 of those jobs to 3 different people. So let's see why this claim holds true. Let's actually maybe just for a start, let's see why it holds true for the first vertex X. For the first vertex U. Actually, that's immediate. So for the first vertex U, U, all of its neighbors have got. You can walk out along any of those. I can walk out along any of those edges incident with U to a vertex in the set B, and that's going to be an alternating path. So we can easily see that all of the neighbors of the vertex U are going to be in this set Y. Why is that true for a generic point X? Well, again, I'm just going to draw a picture. So let's think about a generic point X. So as before, like that. So let's I'm trying to prove the claim. So I'm not going to write so much. The proof is in the notes as always, but I'm going to let X be some vertex in X, and I'm going to be considering the neighbors of that vertex, right? And so let's say Y be a neighbor of that vertex X, right? What I'd like to do is I'd like to argue that that vertex little y is still in the set Y. If I can show you that for every point little x in my set capital X, and every neighbor, little y of that vertex, little x, little y is in capital Y, then I've achieved my goal. Then I've shown that for every vertex of x, all of its neighbors are in y, and that means the whole neighbor set of x is a subset of y. So this is my setup. X is some vertex in my set X, and that means that there's an M alternating path that starts at U and goes to that vertex X. Now, since my vertex, we already know this works for U, so I want to think about another vertex. So if I'm taking another vertex and I look at this some alternating path that starts at U and ends at X, that last edge that we come in on is going to be an edge in the matching, right? So now let's think about, so now I'm claiming that this vertex Y, whatever vertex Y we have, is also, I'm claiming that this vertex Y that's a neighbor of X is in my set capital Y. Why is that true? Well, there are two possibilities. It might be that Y lives already on this path. Maybe Y is here, or maybe Y is here. Well, in either of those cases, you can tell that that vertex little y is going to be in my set capital Y, because I can just truncate this path that I've got, and I've got a shorter alternating path that goes from U to that vertex Y. And that would put that little vertex Y in our set capital Y. So if the vertex Y, if this neighbor Y of X, if that neighbor was already on this alternating path that went from U to X, then I won. Then that vertex little y is going to have to be in the set capital Y, because we've got an M alternating path starting at U and ending at Y. What if it's not? So if it's not in that set, well, then you can just extend. Then you can take the alternating path that I just showed you that starts at U and ends at X and extend by that edge from X to Y. That's going to be a longer M alternating path that goes from the vertex U to the vertex Y. So what we've seen is that in any possible case, this vertex X, all of its neighbors are going to have to be contained in the set capital Y. And because that's true for every vertex X in capital X, that means the whole neighbor set of X is a subset of the neighbor set of Y. And that proves our claim. And again, now combining the claim with the observation gives us the contradiction. So now what I know is the claim is going to tell me that the size of the neighbor set of X is less than or equal to the size of Y, because the neighbor set of X is just a subset of the size of Y. The observation tells me the size of Y is strictly less than the size of X. And that's shown that if we have a bipartite graph that does not have a matching covering A, then there must exist a subset X of A with the property that the size of the neighbor set of X is strictly smaller than the size of X. This is this obvious obstruction, and that completes the proof of Hall's theorem, and that'll complete it for this lesson.